Hello, this is a presentation about the paper Congestion Control Algorithms for Robotic Swarms with a common target based on the throughput of the target area. Why control congestion in a swarm of robots? As the number of robots increases, interferences can occur in the trajectories. The objective here is devise distributed control algorithms to reduce these congestions. In particular, when the robots have common target area, that is, when all the robots need to access the same region, we have more congestion around the target area. This kind of problem can occur, for example, in waypoint navigation and in foraging. Robotic traffic control has been studied for a long time, but few works deal with common target access for robotic swarms. In the current state of the art, congestion problems in robotic swarms are mainly solved by collision avoidance in a decentralized manner. However, just avoiding collisions does not lead to a good performance in the common target problem. Previously, we showed that using only the decentralized avoidance algorithm, the ORCA, creates local minima around the common target region. That is the reason why we are using artificial potential fields here. We introduced a metric for analyzing large-scale swarm robotic systems, the throughput of the common target area. In this work, we defined this throughput as the inverse of the average time between arrivals at the target area. Also, we presented the strategies for maximizing this throughput, which are the inspiration for the algorithms presented here. Two algorithms are presented here: the SQF, the single queue former, and the TRVF, the touch and run vector field. The SQF creates trajectories towards a corridor. Here is presented above the target area. This is the target area. So vector fields creates a vortex-like trajectories to this corridor. Then, when a robot is inside this corridor, they goes directly to the target. Then, when they arrive in the target area, the robots follow a vortex-like force field to make a trajectory, a circular trajectory like that towards the end. Let DPrime be the distance between the robot position and the central line in the middle of the corridor. The influence radius, that is, the maximum distance in which the robot perceives another robot for avoiding congestion. So this influence radius increases proportionally to this distance DPrime. This was made for the SQF being able to deal with small target areas. That is, target areas that has an area less than 5 times a robot area. Here we have a sampled execution of the SQF. In this video we sped up 6 times the original time. Here we see the robots following that force field to arrive the target area and leaving by a vortex force field, like as we can see here with the yellow robots. The next algorithm is the TRVF, or the touch and run vector fields. In this image we show a little of the vortex field enabled by this algorithm. Assume that a robot is located on this position, so this robot is attracted by a force field going in direction to one part of this region. Here we have a force field that makes the robot go to this lane here. Then they follow this lane until they reach this curved path here. Then they arrive at the target area. Right after that, the robot goes in the direction to the exiting lane, like that. Then they are attracted to this line here. Then they follow this line until they reaches the end of the area around the target. Here is a sampled execution, also sped up 6 times. Here we see that the robot goes to the area which is next to the starting position. The robots try to avoid each other by repulsive fields and try to follow the lane. See that the robots that are leaving from the opposite area, sometimes they need to go to the right direction, and this makes the robots go far away before entering the lane. Then they follow towards the target area and try to leave using the exiting lane until they reach the outside area around the target region. We experimented these algorithms using the Stage Robot Simulator. For the graphs that follows, we executed 40 times for each horizontal axis value, and we presented the averages of these values and the 99% confidence interval. First, we compared the number of lanes in TRVF for holonomic robots. Here we compared the values for 3 lanes to 6 lanes, and we see that using 5 lanes is better in respect to the throughput of the common target area. For non-holonomic robots, we see also that using 5 lanes is better for the throughput. We compared the state-of-art algorithms regarding the leaving the target area, the time for leaving the target area, the time for reaching the target area, which reflects the same outcome for the throughput, and also the total simulation time of the execution for the state-of-art algorithms. In this case, we used for comparison the PCC, the EE, and the PCC-EE. So, in this graph for holonomic robots, we see that the TRVF has the least average living time until 260 robots. Then after this value, we see that the PCC-EE is better. For non-holonomic robots, we see that for TRVF we have the same result until 140 robots. Then the SQF is the least average living time from 160 until 300 robots. For reaching time, which is the time from the starting position to until the last robot reaches the target area, we compared for holonomic robots in this graph, and we see that the EE is the better one from 20 robots till 220 robots, but from 240 robots until 300 robots we see that the SQF is better. And for non-holonomic robots we see that the SQF is better from 120 robots until 300 robots. As the target area throughput reflects the reaching time, we see a similar result here, which we have a higher throughput for the SQF for holonomic robots from 240 robots until 300 robots. For the non-holonomic we see a similar result, in which for 100 robots until 300 robots we have the SQF as the one with the higher. For small target area we used robots measuring 0.44 meters cubic, and we ranged the radius of the target area from 0.4 until 1 meter. And in this graph we show the percentage of failure for experiments with 100 such robots, and we see that for PCC, PCC-EE and EE they fail until the radius of 0.8 meters for holonomic robots, and for non-holonomic robots we see that the PCC fails for every experiment, and we see that the EE fails until 0.8 meters. Also we see the same result for PCC-EE. However, the SQF succeeded in all such experiments, and the TRVF was not tested because the lanes cannot be generated when we are using such a small radius. So we summarize as conclusion that based on maximizing the target area throughput, we created two algorithms, the SQF and the TRVF. The SQF outperforms the state-of-art algorithms in time for reaching the target and in total simulation time for a number of robots higher than 280 and 120 individuals for holonomic and non-holonomic robots respectively. And SQF is suitable for small target areas, that is, when the target area has an area measuring less than 5 times the area of the robot. Here are the references that I mentioned in this presentation. Thank you for watching.